What if you were suddenly watching a game of chess where each move unraveled a mystery of the universe? This is the journey of exploring the laws of physics, so well described by Richard Feynman, which makes us think of the complexity of reality as fragments of a chess game that we can only glimpse little by little. On this enigmatic board, each particle, be it an electron, photon, or quark, follows rules that gradually reveal to us the hidden plot behind everything that exists. What if I told you that, just as chess pieces move in predictable ways, there is an even more fundamental rule dictating the cosmos? A simple oscillation can explain the forces and particles that make up our universe. And then come the fascinating stories like that of the Japanese satellite Hitomi, which after astronomical expense and decades of preparation, met its dramatic end due to a failure caused by intense radiation in the South Atlantic anomaly. This event highlights the invisible force of terrestrial magnetism, which operates both in the far reaches of space and in our daily lives, although we often don't realize it. Imagine you're on a beach with a compass in your hand. The simple fact that the needle points north is the result of centuries of exploration and understanding of magnetism, starting with the ancient Chinese who used magnetized stones to navigate the vast oceans. Now fast forward to the 19th century, when scientists like Michael Faraday began to unravel how magnetic fields work around a magnet, drawing lines that we can imagine as invisible threads of force pulling the needle of your compass. James Clerk Maxwell took this to a new level. He wrote mathematical equations that showed that electricity, such as that which lights a light bulb, and magnetism, such as that which directs your compass, are actually two sides of the same coin. It's as if he had discovered that chocolate and powdered milk, when mixed together, always make hot chocolate. Let's talk about an incredible revelation brought about by none other than Albert Einstein, who, in addition to his famous theories of relativity, won a Nobel Prize for unlocking the secrets of the photoelectric effect. Did you know that Einstein described light not as a continuous wave, but as a series of particles, which we call photons? Now think about it. Why is light emitted in defined packets? It's like trying to understand a menu in a new restaurant. You can't order half a dish, you have to choose between the ready-made options, small, medium, or large. In the same way, light comes in fixed portions of energy. If you zoom in on hydrogen atoms, you'll realize that they are incredibly small, about 83 million times narrower than the width of a fingernail. Hydrogen, with its positively charged proton and negative electron, orbits like satellites in space, reminding us of a simplified model of the solar system. These electrons can only occupy certain orbits around the nucleus, just as you can't just pick any seat in a crowded restaurant. Each seat, or energy level, has its own defined size. When an electron jumps to a higher level, it's like moving to a better view in the house. What if I told you that all of reality, including you, can be described simply as vibrations? Yes, we're serious here. Quantum field theory not only suggests this, but also unfolds a universe where antimatter and matter are just the reverse side of the same vibrating coin. Imagine you have a swing in the playground, and there are two children playing at pulling the swing each to a different side, one up and one down. Paul Dirac, a brilliant physicist, told us that the subatomic particles called electron and positron, which is like the opposite counterpart of the electron, behave in a similar way. When these two particles meet, instead of continuing to play on the swing, they collide and disappear, releasing a light that we call photons. Sounds like magic, doesn't it? But this is something completely normal in the quantum universe, where particles can appear and disappear, transforming energy into matter and vice versa. What if I told you that the opposite can also happen? Sometimes this light, the photons, can suddenly turn back into an electron and a positron, as if the magic swing had brought the children back to the game. Exploring this fascinating world further, Julian Schwinger, another prodigy physicist, delved deep into the interactions between light and matter, something he began to study seriously as a teenager in college. He helped develop what we call quantum electrodynamics, or QED, which explains how light and particles influence each other at very small levels. In practical experiments, such as those conducted by Willis Lamb, it has been observed that even small deviations in the way electrons behave around a nucleus can tell us a lot about the fundamental forces of the universe. Even the smallest errors in our measurements, such as those noticed by Cush in the magnetism of the electron, help scientists refine their theories to better understand how the universe really works. And to give you an idea of how precise these studies have become, by February 2023, scientists have managed to measure a property of the electron, the G-factor, with an accuracy of 1 error in a trillion. That's like measuring the distance to the moon with a margin of error smaller than the width of a human hair. This shows just how precise QED is, and why it is considered one of the most accurate theories in the history of physics. Imagine a party where everyone is dancing to the beat of their own music. This party is a metaphor for what happens at the most fundamental level of the universe, where each subatomic particle, such as quarks, gluons, and electrons, dances according to the rules of quantum physics. In 2004, 3 physicists, David Gross, David Politzer, and Frank Wilczek, were awarded the Nobel Prize for Physics for discovering how these particles interact in very specific ways, what they called quantum chromodynamics. They discovered that the interactions that hold quarks together inside protons and neutrons, what we call the strong force, can be described as if they were vibrations in an invisible field that fills all of space. This idea is part of what we call the Standard Model of Particle Physics, which is like a handbook explaining all the known fundamental particles and how they interact. The Standard Model describes 17 types of these vibrating fields. 4 of these fields are for the forces known as photons, light, W and Z bosons, which have to do with radioactivity, and gluons, which hold quarks together. Another 6 fields are dedicated to different types of quarks, and 6 are for leptons, which include the electron and other similar but heavier particles, such as muons and taus. There are also fields for 3 types of neutrinos, which are incredibly light particles and difficult to detect. And then there is the famous 17th field, known as the Higgs field. In 2012, scientists confirmed its existence through the discovery of the Higgs boson, a particle that gives mass to other particles. This was a major breakthrough because it showed that the ideas about these quantum fields were correct, and that in fact, all matter, and the fundamental forces we know are like vibrations in these fields. Now, almost everything can be reduced to these vibrations in quantum fields that interact with each other. I say almost everything because, despite all the successes of the Standard Model, there is still one piece of the puzzle that doesn't fit: gravity. If a theory doesn't work in a place where it should, something is wrong, right? Imagine that scientists are building a kind of giant telescope, but instead of observing distant stars, this special telescope is designed to take a closer look at the smallest things in the universe. This colossal machine is like a super powerful microscope that allows us to see tiny details of reality, so tiny that we're talking about the fundamental things that make up everything in the universe, even gravity. Scientists use this machine to shoot particles at each other at extremely high speeds and observe what happens, which can reveal secrets about how the universe really works. The idea is that this machine can help us understand whether everything in the universe, including the force of gravity, can be explained by tiny ripples or vibrations in fields that are everywhere, but which we can't see with the naked eye. This is part of a theory that tries to show that everything we see and feel is the result of these ripples in invisible fields. This quest may seem out of touch with reality, but it is the dream of many physicists. Since the electromagnetic and weak forces were united in the electroweak force, physicists suspect that a grand unification theory could eventually show that the electroweak force and the strong force were intertwined in a single quantum field. So, until these discoveries are made, Let's keep exploring, questioning, and marveling at the strange and wonderful vibrations that make up everything around us. Who knows, maybe in the not-so-distant future, we'll finally be able to decipher the great mystery of gravity and complete the picture of the quantum universe.